So now let's establish the necessary condition for local extreme point for a constrained optimization problem with equality constraints. So, uh, so we said since we have a constrained set, so the suitable way to compare values of f close to a candidate point. So okay, so suppose that x star is a candidate point, is local, let's say local max, okay, for the problem. So the above problem we set, okay. So we have, of course, g of x star equals c, and we set fx. So yes, we will consider a curve, okay. We will consider xt the family of curve. Okay, oh, you remember? So we will compare along the curves the values of f x star, which is f at x at 0. Remember where xt belongs to s and t belongs to small, yes, small interval e, etc., etc. Regular curve that remains in the constrained set. Okay. Then we need to notice that if you remember ht, we call this is h0. So necessarily, so h prime at t, okay, at t equals 0 was 0. Okay, was equal 0, which is f prime at x0, x star, yes. X prime at 0 was 0. Okay, for any curve, for any xt, okay, for any x prime 0 in the set of all possible tangent vectors. But then that means we have established the following lemma, the lemma that says that each time you have for any y in Rn, so in the subspace, g prime at x star, so yes, for regular points, we set the set of vectors, okay, is exactly the same, the set M that is characterized by this condition, okay. Oh, sorry, for any h or y here, if I did y, so I denoted y, okay, so I will continue like that. So y, what we established each time we took a vector, this is my y, okay, this is my y. For any vector in the tangent vector, we can associate a curve xt that gives us this. Then each time we have this, we have necessarily gradient or f prime at x star, okay, y equals 0. This is what we established, okay. Okay, now still, so this is a characterization, but still it's not practical one to find the candidate point, okay, to find the candidate for optimality. So we need more work on that, okay. So we have the following. Let's continue. There are tools in algebra that will help us. Here it is. So let's continue then, using tools from algebra. Let's denote the matrix G prime at X star. Okay, so it is the matrix formed by the G1, the first component, and you derive it the G1 dxn, and like that we have m component of functions, so we will continue gm d to xm. Okay, so rank, we know that the rank of g prime at x star is m, because x star is, we assume that x star is a regular point. We know to work with regular points, Okay, so we need that. Okay. Now denote also B the vector f prime x star, so the gradient. So it's df dx1, etc. df dxn. Okay, so B is vector of Rn. Okay, then so these the lemma can be written. So we have then for any y in Rn, we can write a y equals 0, imply that b dot y equals 0, dot product. Okay, that is, this is then, so as consequence we can say that the kernel, if we, you know, what is linear transformation related to matrix, so we can say this kernel of E the to the matrix formed by E and B. Then we have theorem so in algebra that relates the dimension of the linear transformation dimension, okay, on the space. So my linear transformation is defined on Rn is equal to the dimension of the kernel plus the dimension of the range which is the rank. Also we can say it's the rank. Okay, so rank of A. But then this dimension, we know it is we said this dimension since the two vector subspace are equal, so it will be the dimension of the kernel of the linear transformation EB. Okay, but this still then the this is always true to say, but so this is equal, so this is true to say it's the rank of EB. So then we conclude that the rank of the linear transform EB is equal to the rank of A. So since this is the case, so necessarily B is a linear combination of rows of A. Okay, so as consequence of that, consequently, as consequence, there exists lambda 1, lambda m, okay, real numbers, such that B is written as, or just here to write things well, so it's transpose of A and lambda. So which gives us that fxi, which we can write, okay, fxi at x star, okay, partial derivative is equal to the sum of lambda g partial derivative gg dxi, g from 1 to m. Okay, so this is now it's, yes, it's and so we have the gradient related to the content, which is very practical now. And if you move this term to the one side, you will get an equation equals 0. So, and this writing suggests the introduction. So introduce now a new function. Okay. So yes, this suggests to introduce the new function. Let's do it here. Okay, let's write it here. Now this suggests for us to introduce the Lagrangian function. So here is Lagrangian. Okay, so we'll introduce the Lagrangian L, x and lambda as fx minus lambda minus lambda 1 g1 of x minus c1 minus lambda 2 g2x minus c2, etc. Okay, minus lambda m gmx minus cm. And then if you look at your the sum we established is exactly if you derive d lambda dl d, or let's write it directly, then the necessary condition, then the necessary conditions, okay, for for x star, a local extreme, a local constrained extreme point, okay, are the following. So we need to have dl dxi, that is df dxi minus lambda 1. You see the sum of all the derivative, so sum from I to 1 to m dgi dxi. So let's set maybe g here, so that, okay, we don't mix the em derivative, okay, the em derivative. Where is lambda? Lambda g, okay, lambda g. Okay, and we have all the partial derivative from 1 up to n. And then for lambda g, dl d lambda dl d lambda g will be exactly minus of g of x minus c, okay, cg. Okay, if you want, we can remove the g, we can just use k so that we don't mix everything. So lambda k gk x minus ck, and we repeat this for k from 1 to m. And you see we have then a system, yes, a system. We have more unknowns, okay. The unknown here are of course the point x with coordinate x1 xn and lambda 1 lambda m. So we have more variables, n plus m variables, okay, variables, and we have also more equations, and n plus m equations. So the system, but it's still more solving, it is reduced to solving systems than comparing using the definition, which is not evident. Okay, so this is exactly or equivalently what we can write is just finding finding the gradient of in x lambda as function. L is a function of two variables, let's say x and lambda. L, the gradient of x lambda, okay, equal to the 0 vector, okay, equal to 0. So this is the 0 vector, okay. So it is reduced to an equation that, okay, an equation. So this is much more practical. So the problem we had at the beginning, a constrained problem, is reduced now to solving a system or finding, or as a remark. So it's we are looking here, we look for how we call them, critical points of the Lagrangian. So this function is called Lagrangian, for the Lagrangian L. Lambda 1, lambda and m are called Lagrange multiplier. Here at this level, we don't. They are just a way we can solve in x and lambda. For a moment, the point is, the most interesting is the x's, but later we will need the lambda to identify globally, to classify the point, whether it is local maximum or local minimum relatively to the content set. Okay, so this is, yes, this is the idea of the idea behind how to solve a constrained problem. Okay, so this is yes, the main idea. Okay, so let's do one example short quickly. Okay, yes, pay attention. So what is important here? Everything worked under what? We assume it to work with regular points. Okay, we needed this assumption so that we can have a tangent vector, and we could establish the theorem. Okay, yes, an example. The examples are long. There are many steps to check, so yeah, I think we stop just here. It's not, yes, as a remark, important remark, it's not an optimization problem, a new optimization, so remark. Okay, so the problem is not reduced to an unconstrained problem. Constrained problem for L. Okay, for L. Okay, so the critical point, but just we look for the critical points of L. Okay. Okay, so it's not, that doesn't mean we are looking for. Okay, and yes, that's all we want to mention, to pay attention to that. Okay, the regularity of the point, regularity condition is necessary for the proof, Maybe there are other theorems, but for this one we strongly use it in the proof, this property. Okay, so this is mainly the idea, and it's beautiful idea how we connected the Lagrange function, connects the function to its constraint. So we are including the both informations, you see, which is very, very nice.